Hello, my name's David Runciman, and this is Past, Present, Future. Today we've got something a little bit different in our History of Bad Ideas series. I'm talking to the astrophysicist Chris Lintott about a theory of the universe, steady state theory. It was pretty fashionable for a while, but it turned out to be wrong. This is a conversation not just about cosmology, it's also about people, and one person in particular, Fred Hoyle, who became the champion of steady state theory. It's a really interesting story about how it's possible to be right and completely wrong all at the same time. Before we start this conversation with Chris Lintott, I just want to say a little bit by way of introduction, because this is a conversation about science, and I'm aware that may not be everyone's cup of tea who regularly listens to this podcast. We're talking about the two rival theories that were at odds with each other, primarily in England, in the English-speaking world, in the 1940s and 1950s, to explain the biggest question of all, which is the nature of the universe. What makes the universe the way it is? One of those theories came to be known as the Big Bang theory, and it's the one that we still call Big Bang today, and it's the one that eventually came to be accepted. Its rival, which was particularly associated with a prominent and brilliant English, Yorkshire-born scientist called Fred Hoyle, was known as steady state theory. The Big Bang said the universe began in a Big Bang. It just exploded out of nothing. Steady state theory said it did not have a beginning or an end. It was constant. And to explain what appeared to be a changing universe, steady state theorists said that the universe produces new matter, new material in order to keep itself in a steady state. That's why it's called steady state theory. So these two rival theories are really at odds with each other. One, the universe exploded out of nothing. The other, the universe might look like it's changing, but deep down, it is constant, it is steady. And the thing to say about these two theories is they're both kind of mad, and they seemed to the other side to be mad. So one of them, Big Bang, says somehow everything came out of nothing. And the other one, steady state, says that change is an illusion, and the universe just carries on forever the way it is. And as you'll hear in this conversation, though there's a certain amount of science in what we're going to be talking about, this argument does have something to do with faith as well. There are crossovers with familiar arguments from religion. Some people believe in creation when it comes to the universe, a moment of creation. And some people believed in a form of eternity, of constancy, of endlessness. And the arguments between the rival scientists were partly questions of faith. So this is also a conversation about something very human, which is why, when, and how do people hold on to their faith? And as you'll hear in the case of Fred Hoyle in particular, why do they cling on to their faith past the point where the evidence seems to have shown it up, to have exposed it? Why do they dig in? Why do people dig in? So this is a scientific argument. It's also a kind of doctrinal argument. And it's a very human story about weakness, frailty, ego in the face of evidence that suggests you might be wrong. Stick with it. It's really interesting, not just about the universe, but about human beings. Chris, we should probably start with some background to explain what it was that these rival theories were trying to make sense of. The Big Bang theory, the steady state theory. As a layman, I think I initially thought they were trying to make sense of the origins of the universe, but I've come to understand that can't have been the puzzle, because that begs the question, because then the Big Bang theory wins. What they were trying to explain was the expansion of the universe. So can you just sketch out, in the first half of the 20th century, how that came to be the central question of cosmology, expansion rather than origin?
Sure, it's really the result that leads to the development of what we would call a science of cosmology, the idea that you can apply physics to the universe as a whole, which is a relatively, the idea, especially the idea that that's connected to anything you might observe or experiment on, is a relatively recent idea. I'll go back slightly further than you asked, to the end of the 19th century, when the big debate in astronomy back then is about whether galaxies exist. In other words, whether the stars that we see around us, which make up what we call the Milky Way, are all there is, or whether there are other, they would have said, island universes out in the cosmos. There's a wonderful quote from a science writer called Agnes Clerk, who was a remarkable figure in the late 19th century, where she wrote a complete history and summary of astronomy up to that point. And she says in the 1904 edition that the idea of galaxies beyond the Milky Way was a long forgotten and discredited hypothesis. But science doesn't stand still, and mainly because of two advances we realized that there were other galaxies. So the universe is populated with these immense systems of stars. And the main thing that happened was that astronomers were able to split light from even faint objects using big telescopes, mostly in the States, into their spectra. And that means you can measure the position of the spectral lines, and you discover that those lines are shifted mostly, though not entirely, towards the red end of the spectrum, what we'd call a redshift. And one interpretation of that is that these galaxies must be receding from us. And so you end up with a picture which slowly builds up over the 1920s, in particular, building on work by something called Vesto Schleifer in Arizona, and then Edwin Hubble comes into the picture a little bit later. You get the idea that most galaxies are rushing away from us. And if you try and imagine that in your mind, then you can explain that by saying that the universe is expanding, that it's rushing away from us. And actually, we can go one step further. So Hubble's great contribution to this was to use the biggest telescopes in the world, first of all at Mount Wilson in California and then at Palomar just up the road, to find individual stars in these galaxies, and to find a type of star called a Cepheid which pulses, and it pulses in such a way that it betrays its real luminosity and thus its distance. So we now have a speed for each of these galaxies measured from the spectra and a distance measured by Hubble looking at these Cepheids. And you discover that there's a simple rule, which we now call the Hubble-Lemaitre rule, which is that the further away a galaxy is, the faster it seems to be receding. So the further away a galaxy is, the faster it's going. So a natural way to explain that is to say that space itself between us and the galaxies is expanding. And so that's the observation which becomes really well established in astronomy in the 1930s, really. And then we need a natural explanation for that expansion. So as soon as I talk about space expanding, if you imagine people standing on a stage which is expanding in all directions, the distance between them gets bigger. But of course, in your mind, you can run that backwards, and there's a point where we're all crammed together in the middle of the stage. If you run the universal expansion backwards, you end up with this point where all the galaxies seem to be very close. And that's the sort of idea that we now describe as the aftermath of the Big Bang. So in some ways, it's a very natural consequence of the observations. Of course, it's clearly bonkers, right? The idea that there was a moment in which all of the universe was very close together, it feels very unscientific. We don't have physics now or then to describe that moment. And it feels like cheating, I think, to many of the physicists at the time. And so the idea that we're talking about today, the steady state idea, is an alternative. It's a way of escaping from that conclusion that if you have an expansion, there must have been a beginning.
My sense of it reading about it is that a lot of what drives steady state theory is a kind of repugnance from the alternative. And among many things that just seemed ridiculous was the idea that something could come out of nothing. If this has an origin story, then in our simple human brains, we have to wrap our minds around the idea that what came before the thing was nothing, and yet out of that nothing came something.
That's right. It's got a sort of theological bent to it, really.
And steady state, we're going to talk about one of the leading advocates of steady state, Fred Hoyle, and we'll say a bit more about him because he's a fascinating figure in his own right. But one of the ironies of this story is that the label for the rival theory, Big Bang, was coined by Fred Hoyle, who was an advocate of the alternative.
It was during one of his broadcasts for the BBC in the late 40s, early 50s, which is the peak of this sort of controversy. I've actually got the quote here, which I think is worth reading. He was a brilliant lecturer. And one of the things that we'll come to in the Hoyle story is that he is somebody who is a popularizer of science. Although he was always very clear in his writing and talking and autobiography that this isn't a noble astronomer coming down to give truth to the people. He was very keen on the money that he was paid for this. So he supplemented his income. But he started off giving these lectures initially on the third program, hoping to reach a few 100,000 people. But they were so successful, they were rebroadcast on the home service. And about 3 million people listened to this series of talks on the nature of the universe. So this is the Brian Cox of his day. But he says he gets to the point where he's talking about these different theories. And he says, on scientific grounds, this Big Bang assumption is much less the palatable of the two, for it's an irrational process that cannot be described in scientific terms. On philosophical grounds, too, I cannot see any good reason for preferring this Big Bang idea. Indeed, it seems to me in the philosophical sense to be a distinctly unsatisfactory notion, since it puts the basic assumption out of sight, where it can never be challenged by a direct appeal to observation. So I think this is the key to Hoyle and his collaborators, in particular, Bondi and Gold, this trio who maybe we'll come to, who have this dislike of the Big Bang because it's cheating. As a physicist, you've got to explain this expansion. You've got to explain how all the matter in the universe came to be. It's cheating to say there was this magic moment 14 billion years ago, we'd now say, where all of that happened. He doesn't see how that's attached to observation. And so there's this sort of distaste for that. And so therefore, you need a model of the universe today that explains those things, that can explain how you have an expanding universe without this moment of creation.
And we'll come on to that model because also as a layman, there's something a bit repugnant about that, the idea that the answer to the question of expansion is in the form of something where the keyword is steady. But we'll come on to that. But Hoyle's other line here, which is quite powerful, I think, he assumed that what scientists were doing was suffering from a kind of Genesis envy or God envy. You know, they seem to have mimicked the theological explanation. And I think he genuinely believed that one of them, it was almost hubristic on the part of science, that one of the things they were doing was kind of playing God in this story.
I mean, I think that's true, although Hoyle himself, who's this brash Yorkshireman who's come down to Cambridge basically and causes trouble for his entire career, falling out with almost everyone, as we'll hear, and doing himself some damage along the way, but a remarkable physicist, a remarkable scientist, a remarkable speaker and writer as well. There's not too much evidence that he thought, I know he mentioned it there, that he thought too much about the philosophy, like the broader philosophical stance here. So I mentioned his collaborators, Bondi and God. These are a trio that came together in the war. They're all working for naval intelligence. They shared a house together in which it sounds like a sitcom waiting to happen. I have to say, there are stories of Hoyle pacing around saying the same thing over and over. Why is it expanding? Why is it expanding? Stories of him sitting behind Bondi, prodding him with a pencil, going, calculate faster, and so on. Anyway, these three were great friends, and these thoughts about a steady state came out of those discussions. But there are two papers that come out at once. Hoyle's is a work of physics. It builds on general relativity to try and describe how this expansion might happen in what he calls a steady state. Bondi and Gold write a paper that's published alongside Hoyle's, which is much more philosophical. It's much more about the argument you make that there shouldn't be a moment of creation that hides this physical intuition. And so I want to draw a slight distinction between, if Hoyle's our protagonist, I think we need to think of him as a practical physicist engaging with this problem, which is why it enrages him. He's got this observational fact. You're right, though, that there is something, to a physicist at least, there's something distasteful just because it's happening everywhere. That there's this magic idea that the steady state idea implies, that matter's sort of galaxies, perhaps particles, appear randomly in the universe at all times, also seems like magic. It seems like cheating. But Hoyle would be quick to say, and he says in his original writing on this, that it's a modest amount. It's about 3 particles of hydrogen per cubic meter per million years. So that's about 1 atom of hydrogen appearing in a skyscraper, he says, every year or so. So that doesn't seem too bad. Like, that's a modest thing for the universe to get away with. So he's not worried about that second problem. He's very happy for there to be a field or some force or some physical mechanism that does this.
So we should say a bit more about that, because that is a key part of the steady state explanation for this. So that there are these two things that seem to be in tension, expansion and steadiness. But the way that they're reconciled is a kind of continuous, as you say, but minor compared to the Big Bang, process of creation. Let's just try and sketch out, how would you summarize the essence of the steady state theory? What is the key in their mind that gives it greater plausibility than, leaving aside the theological and other critiques, but as an observational theory?
Well, they start with what they call the perfect cosmological principle. So we still use the cosmological principle today as the idea that large-scale observations of the universe shouldn't depend on where you are in the universe. So, in other words, you can't get out of a cosmological problem by pretending that we're in some special place. It's an important part of the fundamentals of cosmology. However, the steady staters believe in what they call the perfect cosmological principle, which is the idea that the universe should be the same wherever in it you are, and whenever in it you are. So at all times it should be the same. So that's their first rule. And so from that, you derive the idea that even though it's expanding, matter has to be appearing at all times. And I think it's kind of hard to tell from their papers, but they're thinking of galaxy formation, really. At the time we're writing, we don't really know how galaxies assemble and form. They know that stars in galaxies seem to have a range of ages. So if you believe that galaxies form straight after the Big Bang, that's slightly confusing because why is it still happening now? And so they have an idea of some process by which matter appears in the vacuum of space and then combines to form galaxies over time. And they're able to predict quite clearly if that rate is constant, the rate by which stuff is turning up, and it should be because of the perfect cosmological principle, you can actually predict the range of ages that we should see in galaxies around us today. We should see galaxies that are younger than the Milky Way. We should see galaxies that are older than the Milky Way. And there's some technical argument about whether we can constrain that with the observations at the time. But they don't really get much further than saying stuff should just appear. Hoyle expresses that in mathematical language. He's an excellent mathematician, and he has a field theory which describes in some of the language of thermodynamics and ideas drawn from quantum mechanics how one would do that. And in particular, the problem is how one would get stuff to appear without violating the fundamental rule of physics, which is the conservation of energy. So, you're not supposed to be able to create things out of nothing. And so Hoyle writes later on, in particular, ideas involving some sort of field that has negative energy that you can borrow from to create these things. Now, that sounds absurd, I'm sure, to your listeners, but it's the kind of thing that's going on in quantum physics all the time. These are normal ideas in the physics of the very small, and what he's doing is stretching them to the very large. He'd also point out that the Big Bang people would have this problem as well. They just have to do it all at once at the beginning. So, he never quite takes, as others do, the idea that breaking conservation of energy is a problem here.
Can I ask you a bit more about the cosmological principle? Because on one level, so there's the cosmological principle and then the perfect version of it. So just the general idea, I completely get that. And actually, it applies in my field too. So I work, I'm a historian, but there's a very useful principle, which is sometimes called the Copernican principle, even though it's applied to social science, which is the idea that you shouldn't assume there's anything special about where you find yourself in time. There's a great human tendency to kind of think the year 2024 is the key year in human history because you happen to be alive in it. That's very, very unlikely. It's improbable that you are at the center of the historical universe. But cosmological perfection sounds like a big leap from that to the idea that in all places and everywhere, in space and time, there's a kind of uniformity. So you wouldn't apply that to history, the idea that it's not that you're at a special point. There can still be special points. It's just it's unlikely that you're special. You're not special. But that one, as you described it, that sounds, again, closer to some kind of theological view. Why would you have to start with the premise of perfection? Perfection is a bit like origin. It's just like a big idea. If that's where you start, haven't you begged the question?
I think a key thing here is to realize that we're dealing with cosmology and not astrophysics. So in other words, we're dealing with the science of the universe as a whole. So within the life of any one galaxy, within the life of our solar system or our planet, of course, there are beginnings and ends and special times. There was the day the asteroid hit, which was a bad day if you were a dinosaur historian or scientist or anything else. So, on those scales, I think you're right to draw that analogy. But if we're writing down the equations that govern the universe as a whole, and we have this scientific principle that seems to hold that simplicity is good. The simplest theory that fits the facts tends to work most of the time, although all of those words are nuanced. Then surely we should be driven to a theory that adds in complexity, that adds in change on the large scale. So it's not so much that the Milky Way, that we're not in a special place in the Milky Way or in our lifetime of our solar system, but on a large scale where, we're talking about an observable universe that even then they knew contained hundreds of millions of galaxies. Now we would say thousands of billions. The things that are happening on a local scale are washed away almost. And there's this paradox in physics, which I really love, which is that on very small and very large scales, the science is very simple. So you can write, even in modern cosmology, you can write the equations that you need to determine our current evolution of the universe on the back of one page of A4. Whereas if I need to describe, I don't know, the spin of a cricket ball or the behavior of a cloud above my house in Oxford, I need, a supercomputer in about 6 weeks and have to make all sorts of approximations. So we're in that regime where we're thinking about simple physics and we're trying to keep things simple. And obviously adding in a time step is very complex. There's also this idea of the arrow of time, which Hoyle goes on to work on much later in his career more directly. But we have this problem in physics that the basic equations in almost all of physics don't care whether time is running forwards or backwards. In other words, you can put time to minus time, run things backwards, and the video will look the same. If I somehow record the positions of all the gas in this room and it's bouncing around and I flip that and I show you the data the other way around, you wouldn't know that there was anything amiss. But of course, our lived experience is one which has an arrow of time. Things decay, entropy changes over time. And so you kind of have to put that in by hand on a cosmological scale. Certainly Hoyle felt you did. And so that's a huge change to how we think physics works. And so the idea of a Big Bang, which has this directed arrow where you start for some reason in a low entropy state and progress onwards, that feels very unphysical to him. And so it's better to have a theory that doesn't need to do that, I think, was part of the argument.
In the 40s and the 50s, when these rival theories were sort of duking it out, and Hoyle was getting a real hearing for his steady state theory, were they making these arguments simply on the basis of what was the most coherent account? Or was there an assumption that the search was on for evidence that would prove or at least reinforce one or other of these theories? In the 50s, was there thought that there was going to be a resolution to this puzzle if something or other could be found? Or was it almost going to be a philosophical debate? That was the assumption about it.
Well, I think what's interesting is there are two phases. Let's go through them separately. So the first phase, so by the 30s, we've got evidence of expansion. We have solutions from people like Lemaitre to the relativistic equations that seem to imply an expanding universe makes sense in general relativity. Although, interestingly, most of the people who are thinking about that stuff from a relativistic point of view, the real theoretical mathematical physicists, are quite happy with models that imply an expanding universe and a Big Bang, but they never really seem very excised about that as a physical reality. It's almost a mathematical game. And the thing that forces that into a physical theory is a debate that takes place mostly in the US with people like George Gamow about how elements are formed. We're beginning to understand in the 30s and into the 40s that nuclear reactions in the center of stars produce, or rather fusion reactions are the thing that power the stars, that power the sun, which is a problem that has foxed physicists for about 100 years. But new insights from quantum mechanics show how this can happen. Show that the sun can be a place where hydrogen can be fueled, turned into helium, that releases energy. And they're also beginning to think that there are other ways to do this, but they can't work out a way to make the heavier elements. The temperature at the center of the sun, even though it's millions of degrees, is not hot enough to allow large atoms or atomic nuclei to combine together and form heavier elements. So there's this puzzle of where heavy elements form. And Gamow and others in the States say, okay, well, this must be a primordial formation. We've got the idea of an expanding universe. We've got the idea of this early time when conditions will be very strange. And they say, okay, maybe back there the density is high enough, or a little later on, they realize that the thing they need to change is the temperature. Maybe just after what we'd call the Big Bang, the temperature is high enough that you can form elements there. And they spend a lot of time trying to predict the mix of elements you should see in the universe today based on a period of a few minutes where the universe was perhaps something like 1 billion degrees. And in other words, they found somewhere in the universe where they can put these extreme conditions. Now, that's mostly happening in the States. In the UK, you have Hoyle, and the work that he will forever be remembered for by mainstream physics, working with Geoffrey and Margaret Burbidge, theorist and an observer, and William Fowler, who later won the Nobel Prize for this work, worked out that in the center of more massive stars, and in particular the center of red giant stars, you got higher temperatures. And there's this incredible paper, it's known as B2FH, that still stands as a monument field, where in about 50 pages, they just set out where all the elements actually come from. They form in giant stars, some of them form in supernovae, and we've basically got the modern theory of nuclear synthesis that produces the stuff that leads to this idea that science communicators like that everything inside us is stardust, that we're made in the cores of stars. And so from Hoyle's point of view, he's got rid of the need for this Big Bang. Actually, you still need the Big Bang to create the helium that we see in the universe, but the rest of this nuclear synthesis doesn't happen in the early universe, it happens in stars. And so the two sides come together for different reasons. And so you can see why, when Hoyle's thinking about the steady state, he sees that he's shown that the Big Bang's not needed anymore, that it was this solution to forming elements that isn't necessary because that problem's ticked off. And so that first phase is one about sort of actually understanding where elements come from nuclear synthesis. But it leaves behind this hypothesis of the hot Big Bang.
So that completely makes sense. That makes the steady state, actually, I can see the hold of it on someone like Hoyle, because you've got people who have this place where they put the problems they can't solve, which is the first few minutes of the universe where everything is so hot and weird and mysterious. We don't understand it, and therefore it's our explanation. And here he comes along, it's presumably relatively young man, and a kind of scientific genius. There's a genius to this explanation. And he says, that place where you dump your problems you can't solve, I've taken it out of that place and I put it in a space that we're all comfortable with, the kind of science and physics that we're comfortable with, and I've solved it. I mean, that's a pretty strong calling card for steady state theory. So when then in the 40s and 50s the argument was being had, how many allies did he have? How would you assess the sort of state of the game in the 50s? Who was winning?
So it's interesting. So the radio broadcast with his disdainful Big Bang was late 40s, I think into 1950 when it's rebroadcast. That's when his papers have come out in 48. And it's very easy to get the sense now that it's a very small coterie of people, because it's this bunch of people mostly in Cambridge, plus allies like the Burbages and so on, clustered around Hoyle's Institute of Theoretical Astrophysics. He set up his own institute in Cambridge because he's fallen out with the people in the Department of Physics at the Cavendish. So there's also this university politics going on. And it is this small cluster of people, all of whom will go on to affect astrophysics in all sorts of ways. But you have to realize cosmology was not a core pursuit then at all. So today, we think of cosmology as core to astrophysical sciences. It's only just becoming established, only just connecting to observations. And so it is a British school. It's disliked by the American school around Gamow and so on, who don't really see this continuous creation. But it's this core of about 10 people who are the steady staters. There's a key figure at the Institute at the time who's a bit younger than Hoyle called Dennis Sharma, who'd go on to be the supervisor of Roger Penrose, to work with Martin Rees, who's now the Astronomer Royal. And he's a pragmatic observational type. He's somebody who stayed connected to what was happening in observation. And he was very much on the steady state side. So it's not just this game being played by Hoyle and friends. It's utterly mainstream in cosmology. But in the 50s, it becomes clear that you can test this idea because it makes very strong predictions. And it's very simple. It goes back to this principle. Nothing should change in the universe if the steady state theory is correct on large enough scales. And because astronomers have this marvelous ability to make use of a natural time machine by looking at the distant universe. We know when we look at the distant universe, we're seeing things that are taking a long time for their light to reach us, which means we see them as they were millions or often billions of years in the past. So we can directly look at the universe as it was 1, 2, 3, 4 billion years ago. And that begins to be the test. There's also, I should say, there is one set of evidence on the table already in 1950 that's very important, and it favors the steady state. And it's called the age problem often, or the time problem, which is that we understood by then, had understood for a long while, that the Earth was billions of years old from things like study of radioactivity. We had a good understanding of stellar evolution, and so people knew roughly what the ages of stars were, or at least that there were many stars in the galaxy that were billions of years old. That fits with the geological record, so that's nice. But the Big Bang theory, worked out using the measurements that Hubble and others have made, suggested the universe was only a couple of billion years old. So we had a universe where things were older, things in it were older than the universe itself. Obvious nonsense. And so the steady state doesn't mind that at all. We can have continuous creation of so on. So the observational evidence, I think you can argue in the late 80s that if you're a pure observer like Sharma or some of the others, then you're completely at liberty, I think, to say that the evidence favors the steady state. But that's at 1950, and then things change quickly.
So let's go through the change, because the thing that I'm then interested in is how and why Hoyle sticks to his guns past the point where the evidence has shifted, because that's a fascinating psychological question that we'll come on to. He's an extremely interesting figure. But to get there, we need to know what it was that shifted. And crucially, I think the decisive shift is in the 60s, isn't it?
Yeah, that comes a bit later, but the rest of astronomy moves before then.
Okay, so take us through the phases by which the steady staters go from being a rival camp to basically a set of cranks.
So they predict that the universe should be the same. It turns out that this is particularly important when we start doing radio astronomy. When we start seeing distant galaxies in the radio, it turns out that if you just count up the number of radio galaxies that you see at different fluxes, so different strengths, so how many bright ones you have, how many slightly fainter ones that you have, how many really faint ones you have, there's a really, really, really clear prediction from steady state as to exactly what that relationship should look like. There's no equivalent prediction from the Big Bang. It's not that if it's minus 1.5, it's steady state, but if it's minus 3, it's Big Bang. But the steady state says the gradient, these things, the way you fit these things should be this number, minus 1.5. And in Cambridge, remember, Hoyle's fallen out with the Department of Physics. The Department of Physics is the domain of radio astronomers in the UK, along with Manchester and Lovell. But in Cambridge, they're doing big surveys of the radio sky using rescued equipment, mostly from German radar installations that have been repurposed and requisitioned, possibly in a slightly shady fashion by people like Ryle and co, who build these enormous arrays of antennae. And they start counting the number of radio galaxies. And this is, I think, where it goes wrong for Hoyle, because what's called the second Cambridge catalogue, to count these things, is announced with great fanfare. And they say that the slope that they've measured is inconsistent with the predictions of the steady state. Hoyle's theories are dust. He's obviously wrong. Why would anyone listen to it? It's quite, it's presented as definitive. And then there's news from the Southern Hemisphere, where Sydney have been doing this as well. And the results in the Southern Hemisphere are not so conclusive. In fact, they disagree with the Cambridge results. In fact, they show the Cambridge results are overconfident. They've basically, in trying to pick out these signals, in radio astronomy, you're always fighting the fact that the universe is noisy. There's so much interference from cars and power lines and trains and human interference, plus the natural background. This is a difficult job, and they've been too confident. Many of the things they've identified as radio galaxies are probably just noise. And so Hoyle and co jump on this and say, look, obviously these results are nonsense. You haven't concluded anything. You've criticized us unfairly, and it gets quite nasty.
And presumably he says, and these people hate me, right? I mean, it presumably gets very personal.
Yeah, that's also true. Certainly in correspondence, he's very angry about it. He thinks that it's because he's popular. He blames it on his profile as a science popularizer. And it's certainly true that those 1949-50 talks were criticized. He was a junior research fellow, and he was presenting on the BBC to 3 million people his ideas as if they were essential. I don't think he did anything wrong, but he certainly felt persecuted. All sorts of Cambridge politics comes into this as well. Arguments at the Royal Astronomical Society, all carefully minuted. But he thinks, look, these radio astronomers don't know what they're doing. There have been arguments amongst the groups before, even about what these things are. And so this continues as the radio astronomers produce more evidence. So there's a third and there's a fourth Cambridge catalogue that really do show that the result that they get is slightly different from that predicted by steady state. But Hoyle and Bondi and the others aren't having any of this. Even Sharma is saying, look, it's only slightly different. You said it was way off, and now you're saying we're only slightly different. Surely there's another error in your calculation somewhere. Surely we can move a bit, you can move a bit. They don't see it as definitive, but the rest of the astronomical world does. And it seems like an unfair test, I think, to Hoyle. You can see in his writings from the time that he's pointing out that it's not that there's a prediction from the Big Bang side. They just say that they don't know. Any result you get would be compatible with the Big Bang. It's very, very frustrating. The analogy, I think, these days is something like trying to test string theory with the Large Hadron Collider, where if we found particular particles, string theorists would be vindicated, but their theories are perfectly compatible with us finding nothing at all. And so you get these debates about whether that's even science. And I'm sure that's how it felt to Hoyle. There's a crucial piece of evidence that's missed in the historical record, which is actually early work by Martin Rees. His supervisor was Sharma, and he said, okay, never mind radio. This is obviously difficult. We're now finding these quasars, these quasi-stellar objects. These that we now know, the cores of distant galaxies seen shining as material falls onto their black holes. And they do the same trick. They go and count the number of quasars at different distances. or rather at different luminosities. And they discover that even putting aside all the optical radio stuff, putting aside all the animosity with the people in the Cavendish and their field outside Cambridge, putting aside all of that, you get this result that shows that the universe changes. There are more of these things in the past than there are today, undoubtedly. And that really loses Hoyle's support. So Sharma switches sides remarkably. No one new after that starts working on this in a serious way. But Hoyle is left with his theory. And then in the 60s, as you say, what most people will say was the definitive evidence was the discovery of what's called the cosmic microwave background, which is the light that was emitted during that hot phase just after the Big Bang. So this is light that's been traveling towards us since about 400,000 years after the Big Bang. We see it in the microwave region of the spectrum, and the shape of its spectrum can be precisely predicted from a Big Bang model. And they even get the temperature of the radiation that we see today right to some accuracy. And at this point, I think this is the point where the steady state goes from being an alternative to being really a crank pursuit, or at least it loses its elegance because Hoyle's models, working with other collaborators, start to involve things like a magic form of dust that fills the universe that happens to emit this microwave background radiation. And so you need dust with exactly the right properties to do this. Actually, we went through this again recently. We discovered the expansion of the universe was speeding up, and for a while those observations were explained by grey dust that had just the right properties to. So this is, a standard astronomical move. We always say you can blame everything on dust or magnetic fields, but by the time your beautifully elegant theory involves you to invent a new type of thing that emits radiation at just the right way to mimic your rival's natural consequence of their theory, you begin to get a bit touchy. And it's the microwave background that really, I think, establishes the idea that the universe was once in this hot, dense state just after something that we call the Big Bang.
And that does sound like the key shift in the sense that, so I can see if you're Hoyle and you're being shown that your predictions are slightly off, but the other side don't have predictions at all, you're going to dig in. But when your predictions are more than slightly off and the other side's predictions are being borne out, so that presumably is the key thing about the cosmic microwave background. For the first time, the big bangers are able to do the thing that Hoyle had assumed they would never be able to do, which is have predictive hypotheses borne out.
Exactly. And around the same time, they've also worked out that you can predict the ratio of hydrogen to helium in the universe, because you do forge helium in these hot conditions. And so you can disprove the Big Bang today by finding a part of the universe that has less helium than we think was predicted in the Big Bang. So they also have that. It's important to realize a lot of this was fought out sporadically, but often in the public sphere as well. The first report of the microwave background was on the front page of the New York Times above the fold before it appeared in a journal. There's a remarkable incident with the Cambridge group, with Ryle and so on. I talked about the second Cambridge catalogue, there was a third, then there was the fourth, which had the definitive proof. And Ryle, it's not clear whether he knew what he was doing, but ended up presenting his results in a press conference at the Mullard Space Science Lab outside Dorking, down in Surrey. And Hoyle was invited, and when he got there, he discovered he had a seat on stage. And so he'd brought his wife with him. She sat at the back. It was just him. Spotlight on him. Ryle presents his results with graphs. There's a blackboard. And he says, so clearly we've disproved the steady state of the universe, and turns to Hoyle for a response. And Hoyle gets out there as quickly as he can. Is hugely upset. They go to the Royal Astronomical Society in Piccadilly, where they can buy on the way into the meeting a copy of the Evening Standard that says biblical universe is correct, because they've interpreted this as, a moment of creation happened. About 5 minutes of creation, they say, for some reason, from something that Ryle said. But that's how public this was, right? So this is, and Hoyle was the best known, certainly physical scientist of his time. And so you have to realize he's also in public defending these things. And Ryle ended up apologizing to him for the way that happened.
If you were Hoyle, you would think it was personal. I mean, that sounds like it's engineered to humiliate him. They don't have to have him on stage. In any other context, you would think that a warning that this was going to happen would be the minimum sort of civil thing to do. So if he was paranoid, maybe it's because they were out to get him a bit.
I think so. Or, he's an interesting character, I think, because he has this intense, well, maybe not paranoia, but feeling that he feels his papers aren't being read. There's this wonderful description of reviewers doing their work silently in the dark like owls to put him off. His theory, it's not so much that people disagree with him. I think he'd be fine with that, but he can't get people to take his theories seriously. He doesn't understand why he doesn't have more people working with him and so on. But yet from the outside, you can also see he's got his own institute at Cambridge. He's funded to do the research that he wants to do. He basically has the power of patronage and can hire anyone he likes for a while, certainly right up until the late 60s. And he's this public intellectual with a megaphone. So I do wonder whether some of it was that people assumed he'd be fine. This is a person in the center of academia with all the privileges that Cambridge can bestow, basically. Everyone's ideal job, running your own institute and thinking only about research. And yet, he does have this vulnerability to him as well.
He then came up with what I've seen described as the quasi-steady state theory in order to keep this thing going, to keep it propped up. It feels odd to be so committed to it that you're willing to, at the risk of ridicule, keep it going in a very diluted form and to fall back on the devices that were the thing that you criticized the Big Bang for. So once you're with magic dust or whatever it is, you're finding your little space in which you can dump the problems that you don't know how to solve.
Yeah, it's rather hard to describe the quasi-steady state theory because it's complex. It's deeply mathematical. You can think of it as sort of bubbles of creation happening all over the universe, sort of mini bangs, and we end up to be in a rather special space, as it turns out. So you throw that out as well. Comes back to what I said earlier on, which is that, remember, Hoyle wasn't the one driven by the philosophy here. He's driven by physics and a bit of rivalry and so on. So I can see why it's Hoyle that ends up doing this, but he works for about 10 years on this theory. He ends up publishing a very dense Cambridge University Press book that's published with his working on this theory, which even at the time they published saying this will be of use to historians of science. We don't expect anyone to deal with it now, though it did sell. It sold a few thousand copies, which was unheard of at the time. But the theory is basically ignored. It's not that anyone even bothers to disagree with him at this point in the 70s. That people are just, he's got one or two people working on this with him, and that's it. That's the crowd of people. But it also, the end of that then marks quite a strong departure for Hoyle, I think. You can see that's all may not be the most interesting or useful or mainstream contribution to cosmology, but it's still cosmology. He's still doing physics. And then after that, he ends up both within his field and beyond it, lost in a rather strange set of very fringe ideas, which in cosmology manifest themselves as sort of attacking, going right the way back to the beginning and attacking the evidence for the expanding universe in the first place, working with somebody called Halton Arp, who was a famous galaxy observer. They start to unpick the idea that this redshift tells you about distance. They think they've seen galaxies that are near each other that have different redshifts, and thus should be many billions of light years apart, but they think they can see connecting bridges between them. And if that's true, though, all of cosmology falls apart. And so Hoyle at this point goes back, having always been somebody who follows the observational evidence, admittedly with rather increasingly complex theories. He goes back to being somebody who doesn't even believe the evidence of the images that the telescopes are producing. And that, as a scientist who admires Hoyle, that's the sad bit of this for me. The quasi-steady state is a heroic attempt to tilt at a windmill. After that, it's not even very clear that he's thinking scientifically about the problem.
Yeah, I was going to ask you, because psychologically, it's a familiar story in many ways. So here you have someone who, as a young man, was a bit of an outsider, a bit of a maverick, and then he came up with ideas that were rejected or seemed fringe, and they became completely mainstream. So you're going to have a bit of a Messiah complex or something. You're going to believe that when they're doubting you, maybe that's evidence that you're right. But as it goes on, I think you're being polite. They weren't just fringe ideas. They were bonkers, right? Some of the things that he was saying towards the end.
Well, in cosmology, they were fringe beyond the rest of it. So, yeah, particularly in the late 70s. So he starts thinking about origins of life and has the idea that life is distributed. And there's almost a quasi-religious aspect to this as well. So there's this idea that the universe seems to be what he called a put-up job. Like, there seems to be evidence of design somehow here. And it goes back to his work on stars. There are certain atomic fundamental constants of the universe. This is a whole different podcast, but that need to be the way they are for stars to be able to produce heavy elements. So he starts to think about the need for a universe that's full of life. And so he says, okay, so life can be distributed on comets that travel between solar systems. Not crazy. We've seen 2 objects so far, but we will see many more objects that travel between solar systems. It's not even crazy that comets bring chemistry to Earth. We think that most of the water on Earth comes from the impact of comets and perhaps even asteroids. But along with a collaborator called Wickram Singer, he has the idea that bacteria are being carried amongst the stars. So things as complex as single-celled organisms. And further, that every time there's a new disease, in the 70s, Legionnaire's disease was discovered, flu outbreaks, for example, those clearly come from space. So there's this remarkable popular book in which he does a study of flu outbreaks in schools in Yorkshire in 1978 and tries to use the data on which kids were not at school on which days to demonstrate a spaceborne thing. And he believed this to the end of his life, and his collaborator's still around and still believes this.
And linked to sunspots, right? Which for some people is the mark of the crank, right? You connect your theory to sunspots. Flu plus sunspots equals Yorkshire school attendance. That sounds right on the edge.
Yeah, that's right, because your sunspots are on an 11-year cycle. So lots of things. There was a period, it's not true anymore, but right up until the middle of the last decade, going back to your world, there was a very strong correlation between sunspot number and the proportion of vote for Conservative candidates throughout the 70s, 80s, and 90s in UK elections. That's devolved. Maybe the sun's changed. Who can say? It hasn't. But yeah, so there's that strand of sort of what he would call panspermia that becomes very public because he's writing for a popular audience. There's definitely some sense that he needs the money. He quit his Cambridge job in high dudgeon in the late 60s, not because of the steady state, because of internal politics, and was a sort of academic for hire, and had arguments about this. He's a very anti-Darwinian thinker. He doesn't believe in the Darwinian theory of evolution. And so he gets embroiled in a row with the Natural History Museum in South Kensington about whether their Archaeopteryx fossil, which is obviously a bird-like dinosaur with feathers. He says the feathers have been added in, that it's a fake, that somebody's pressed feathers into the clay, writes a popular book about that, provokes the museum into doing a whole exhibition called Archaeopteryx, Is It a Fake? To which the answer is no, and they demonstrate why. But it really damages his reputation. But it is at least possible at this point he's chasing money. He's trying to write popular books that sell, as well as to get his ideas out there. And so this, I think, is the bit of Hoyle's life that we don't like to remember, because he embodies the sense that lots of us have. There's an odd joke around about aging physicists who suddenly think they can solve every other field as well. And he sort of embodies that in his biography, because he wrote a rather wonderful scientific biography, which I recommend. It's very interesting. So he published 200 papers on these sort of fringe topics during the late 70s, 80s, and into the just before he died in the early 90s. 200 papers, that's a large proportion of his output. I think it's more than half. And in his biography, he devotes 2 lines to it at the start of a chapter about climbing mountains. And so I think he was aware, at least later in his life, of which of his ideas were important. But that didn't stop him picking fights about all these other things.
Because in some ways, as you said earlier, there's something heroic about it, but not the really crazy stuff at the end. But there's something heroic about the defense of steady state. Actually, particularly, as hearing you lay it out, you can understand why someone might want to dig in at various points, because Big Bang, for all the fact that we all accept it now, those of us who don't know the ins and outs of it, we've just taken it for granted that it's won the argument. There is still something, when you start to think about it, that messes with your head. And you can see why someone who particularly was right early in his career against the Big Bangers might cling on to it. There's something comic about it too towards the end. He is a semi-comic figure, but it's also tragic because his reputation, he did pretty much trash it by the end, didn't he? I mean, maybe it's come back now and that phase has gone, but he was playing fast and loose with his central scientific reputation by the end.
Yeah, it is coming back now, but he burnt it to the ground, essentially. I am old enough to remember that people didn't like talking about Hoyle. It was an embarrassing story. It wasn't something, for one of the greatest minds in British astronomy of the last 100 years to not even be in a case where we can talk about him is upsetting. I think it is heroic, and I think one thing I want to make sure I've said is that without the steady state and without Hoyle's, let's say, forthright advocacy of it, it's not clear to me how far conventional cosmology would have got before the microwave background. A lot of the advances that were made were done in response to goading from Hoyle. You need 2 theories, right, in order to force people to work harder, to keep themselves honest, to make scientific progress. And we do have this profound mystery about the Big Bang. It's still a model, I think, that makes little sense as a physicist. What happened in that first moment? Once you've allowed me the Big Bang, we have a very good theory about what happens next, but it does have this central moment of mystery. And I think one of the strange things about being an astronomer talking in public and in popular culture about this is that we teach 5-year-olds the Big Bang somehow. It somehow gained this. People have the idea that it should be common sense, and that if it doesn't feel like common sense, they don't understand it. But scientifically, I think Hoyle's still right in that we've swept the problems we don't understand into this moment. What's happened since, though, is that the evidence has built up, and it's very hard to get away from the conclusion that there was at least this moment where there was a Big Bang or something like it.
As I was reading about it before talking to you, I did find myself thinking, in many ways, this is still Hoyle's story for two reasons. One, the name. So why do we teach it to 5-year-olds? You try and teach 5-year-olds something called steady state theory, and you're not going to get very far, right?
Or quasi-steady state theory, of course.
Or quasi-semi-state theory, or talk to them about the cosmological principle. So Big Bang, it's a childish name because it was derogatory. And they should be grateful. They should be incredibly grateful to him for having given them the name that goes into primary schools.
Yeah, in the early 90s, Sky and Telescope magazine, which is the big popular magazine on the subject, tried to run a contest to rename the Big Bang because it sounds silly. Like, why are we researching something called the Big Bang? Seems ridiculous. There used to be a sausage restaurant in Oxford called the Big Bang, and that seems appropriate. But they got 5,000 entries from school children and amateur astronomers and professional astronomers, and the jury they put together, which included some quite highfalutin names, all decided that the winner was Big Bang, because there was nothing better than Hoyle's dismissive term. So that has stuck, but also just the idea that there's something odd about it, I think we could take from Hoyle and carry that forward.
Exactly. That was the other thing I found myself thinking. So trying to understand steady states is not an easy thing to understand, continuous expansion. And it starts to look ridiculous because the answer is, as you say, in the quasi version, just lots of little Big Bangs. But the Big Bang itself, not only the mystery of the first few seconds, but the something out of nothing idea, it's impossible to wrap your head around it.
Right. And that balance between which distasteful change to physics you want is something we stick with today. So you may know that we have this problem that most of the matter in the universe we think is in a form we don't understand, and we call it dark matter. Or we try and fiddle with gravity to get rid of the need for dark matter. And basically, people split into camps based on aesthetic taste. Would you rather there be a type of particle we haven't discovered yet, or would you rather that gravity was different? And you can make a technical version of that argument, but basically it's taste, just as it was with the Big Bang and the steady state in the late 40s and early 50s.
So that was going to be my last question, which is, if you look at the field today, Big Bang is, so the name has stuck. No one can come up with an alternative name, and it is the default from which other explanations have to follow. But how much is it still being used in the way that Hoyle suspected it was being used, as a kind of dumping ground for the problems that there is currently no solution to? And is there a possibility not of an alternative to the Big Bang, but of a refinement of it or a modification of it, which is a significant step forward in the way it was a significant step forward from what came before?
So I think the idea that we had this hot, dense phase in the universe is very well established. But before that, in the first tiny fraction of a second, there's this idea called inflation, which is that in that very first moment, the universe undergoes an expansion that's much more rapid than anything we've ever seen since, that is almost unimaginably rapid. And if you add inflation to your theory, it's an idea that's been around since the 80s, then we can explain several features of the universe that are otherwise mystified, like the fact that it looks the same in all directions, and questions about the geometry of the universe as well that Hoyle and others would have tackled. And I think that's a point where Hoyle, if he was still here today and still connected to these things, would be prodding at, because there is no direct evidence for inflation. There are only the problems that it was invented to solve. And similarly, there are ideas from looking at the cosmic microwave background that we may see a signal that would tell us that inflation happened. But equally, its absence doesn't seem to disprove the theory. The theory is fine. And it's just exactly in that same sort of state where I think we need a Hoyle every so often to goad us into getting better at finding ways to test these ideas. Because that's what he did for the Big Bang. He made it an observational science by insisting that they demonstrate its veracity.
And also you need a Hoyle because you need a better name than inflation. When I hear you talking about it, you know what it makes me think? And so I find myself thinking, first problem of inflation is you need a Hoyle to come along and give it a primary school label, because it's not a good enough name for something that is the deep explanation of the deepest mystery of all. You need something better than inflation.
Yeah, we're very bad at naming things. So I think, yeah, we'll give that to Hoyle as well. Even though his paper on star stuff, on how heavy elements are created, it's got a great nickname. It's known as B2FH, Burbage, Fowler, and Hoyle. It's the only paper I can think of that's just so well known that people just refer to it by its initials. He had a taste for branding, I think, which helped.
We have a new bonus episode to go with this series, The History of Bad Ideas, and it's available now on PPF Plus if you'd like to listen to it. You just need to sign up to PPF Plus, which you can do by clicking on the link in the show description or going to our website, ppfideas.com, and you will get all of our bonus episodes. There are loads of them available now. They'll all be there for you as soon as you sign up, and all our future bonuses too. This one is a conversation between me and Lucia Rubinelli, the historian of ideas and our guide to the leopard a few weeks back, about a big idea with a complicated history. The idea is sovereignty. It comes from the 17th century and we try and make sense of its story since then. But here's a little taster of why it gets me a bit agitated when I think about sovereignty and politics today. Brexit happened and the British state, through the sovereign authority of the British people, reasserted its right to take its own decisions. I don't know, whatever that argument was. But there was no discussion about the how. No, we just went back in Britain to taking decisions the way we'd been taking decisions before. It's as though the people exercise their sovereignty in the act of choosing B, not A, B being Brexit, A being Remain. But really, the power of the people ought to reside in trying to reimagine then how you want the state to function, how you want it to operate. What power do we want Parliament to have? What powers do we want to be devolved? What kinds of democracies do we want? Are we still happy with this representative system? Do we want more referendums? Do we want more direct democracy? All of the questions about how power is exercised. But somehow the idea of sovereignty collapsed all of that just into the decision to choose this rather than that. To hear the full conversation and everything that Lucia has to say too, sign up now to PPF Plus, and a reminder, you get ad-free listening as well. Coming up on the History of Bad Ideas, we've got 2 more episodes to round off the series, and we're going to be talking to 2 of our guides this year to contemporary politics. Robert Saunders, who helped us through the history of British general elections, and Gary Gerstle, who was our guide to American presidential elections. I'm talking to each of them about something that probably has gone wrong, respectively, with British politics and American politics. Robert's bad idea is having party members choose the leader of the party. Think Jeremy Corbyn, think Liz Truss. Gary's bad idea is presidential leadership debates. Think of what happened in 2024. First up, it's Robert. Next time. Do join us for that. This has been Past, Present, Future, brought to you in partnership with the London Review of Books. Past, Present, Future is part of the Airwave podcast network.